Hello students, welcome back. Now let's take a short break from that group theory and instead let's have some discussion on some selected topics from number theory. The first topic here is the division algorithm, and everybody knows the division algorithm, I think, but can you prove it? Well, that's something we are going to do here. Given pair of integers a and b where b is strictly greater than 0, in other words, a is arbitrary integer and b is arbitrary positive integer, then they exist unique pair of integers q and r such that a is qb plus r, as I just highlighted in blue, where r is greater than 0 but less than b, as I highlighted in green. Do you remember what those q and r are called? They are called the quotient and remainder respectively. A is called the dividend, b the divisor, q the quotient, and r the remainder. And r is equal to 0 if and only if b divides a. Well, that proof is left to the students. It's not too bad. Let's focus our attention to the proof of this conclusion. The existence of q and r and their uniqueness. The proof is actually really hard. It consists of 3 steps here according to this proof. There can be other proofs too, but this is the version I know. Step 1, we're going to define q and r appropriately so that we have the first half of the conclusion with an additional property. Step 2, we'll use that additional property to prove the second half of the conclusion. R is greater than or equal to 0 but strictly less than b. And then we're going to prove the uniqueness as a separate new problem. That's the plan. Okay, let's begin step 1. Ready? Let's begin with a mysterious subset S of W. W here is a set of all whole numbers, 0, 1, 2, 3, 4, and so on and so forth. So those are non-negative integers. Whole number y in this form, a minus bx form, where x is an integer. A and b are already selected here, and y is a whole number, so this had better be greater than or equal to 0. You see, that's in W, that thing here means greater than or equal to 0. Let's see, is this possible? Is this possible? It turns out yes. If I select x very negative, then a minus bx is going to be very positive and certainly greater than or equal to 0. You see, x is very negative and times negative b, and b is positive, so negative, negative, positive. So this whole thing is going to be very, very positive. And no matter what a value we have, for sufficiently large x value, it's going to get bigger, 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 so that overall quantity will be greater than or equal to 0. And there are going to be many, many such x values out there, and consequently many, many y values out there. So this is a non-empty subset of W. Consequently, it has to have the smallest element, the minimum. Remember, W is a well-ordered set. Every subset has the minimum, the smallest element. And let's call R as the minimum of this. And please note that I just highlighted in green, and that's going to be the special property that I'm going to utilize to prove the second half of this conclusion. The first half is rather straightforward because this set S was defined in terms of y equals a minus bx, where x is an integer and y is a non-negative integer, whole number, and then r is a special case, so r goes here in place of y, and then a certain x will be there, and that's going to be defined as Q. So what do you have? R equals to A minus BQ. Flipping BQ to the other side, we have the first half of the conclusion. A is QB plus R. So first half wasn't too bad. We start from this mysterious set. That's hard part. And does it make sense? Well, we went through that. By selecting x sufficiently negative, we can make this y equals a minus bx greater than or equal to 0. So yes, that's not an empty subset of w. There's a minimum, namely this r. Then r should be a member of this because it's a minimum. Minimum belongs to this, remember? So r is a minus bq, consequently a is qb plus r. And we have the first half of this conclusion plus alpha, plus this green. Minimum always exists, so we have the existence of R and Q, and consequently we have R and Q, so that A is QB plus R. We got this. Existence parts, okay, we have it. But then again, how about the second half? Well, let's talk about it. For the second half, we're going to use the proof by contradiction. By definition here, R has to be greater than or equal to 0, as I just highlighted in red. You see, we began from the set of whole numbers, non-negative integers, 0, 1, 2, 3, and so on. And R was selected from there, so R has to be greater than or equal to 0. No problem there. So this part, that part's done. That part is done. How about the other part? R is less than B, that part. Well, for that purpose, let's assume the opposite. Let's assume R is greater than or equal to B, and we'll try to find out the contradiction. R is greater than or equal to B. Does it help? It's going to be really hard to see anything, so let me give you a hint. R is greater than or equal to B, so that R minus B is greater than or equal to 0. So this here, R is greater than or equal to B. Consequently, R minus B is greater than or equal to 0. That's what we got. Does it help? Does it really? Well, I don't blame you if you don't see anything here. Let me give you a further hint. R minus B is less than R because R subtracted by a positive integer. Yeah, B is positive. But then again, please remember R is A minus BQ. So algebraically manipulate, break a parenthesis and factor B out. What do you get? A minus B times Q plus 1. So we are in this kind of form. A minus B x form, some integer form. And then R minus B is greater than or equal to 0. So A minus B times some integer is greater than or equal to 0. That means R minus B belongs to the set S. Is that a contradiction? Now I hope you can see that. R minus B belongs to this set, yet R minus B is less than R strictly. And R is supposed to be the minimum of the set S. R minus B belongs to S, but it's less than the minimum. There goes a contradiction. R is the smallest element, but I found something even smaller inside this set. So there goes a contradiction. And how did he end up with this contradiction? Well, this assumption is wrong. So R has to be less than B. we assumed R is greater than or equal to B, and that caused all this mess, so that's got to be false. So R has to be less than B. So what's the conclusion? We now have this part as well. R is greater than or equal to 0 and strictly less than B. Okay, we have both blue and green. Now let's prove the uniqueness. Let's suppose there are another pair. There are two pairs, Q1 and QR, and Q2 and R2. And they both satisfy the conclusion. In other words, yeah, they both satisfy blue, and they both satisfy green. A is QB plus R, that works for Q1, R1, and A equals to QB plus R1 works for Q2, R2 as well. And then both remainders are greater than or equal to 0, less than B, both blue and green. Now let's make this observation. If R1 and R2 are the same, this one and that one are the same, then we can cross those out, and you're going to get Q1B equals to Q2B after crossing, and then divide B out, you're going to get Q1 equals to Q2. Yeah, I can divide by B because B is not 0, it's strictly greater than 0. So whenever R1 and R2 are the same, then Q1 and Q2 are the same as well, so these two pairs are actually the same. That's precisely what we wanted. That's how you get the uniqueness. Suppose they are two, but they are the same. Now, what if R1 and R2 are different? In that case, without loss of generality, we can assume one is less than the other. R1 is less than R2. If R2 is less, then just rename those. And then from here, this blue, flip this Q2B to the other side and R1 to the other side. That's going to give me the right-hand side. Q1B minus Q2B is equal to R2 minus R1, and then factor B out. So we got some integer times B is R2 minus R1. Consequently, B divides R2 minus R1. Is that a problem? Yes, because both are positive integers, and B times some positive integer is R2 minus R1, and the smallest possible positive integer is 1. And then if you have 2, 3, 4, and so on, then R2 minus R1 will be bigger. So at worst, they're the same or bigger, so B is less than or equal to R2 minus R1. And in turn, R2 minus R1 is less than or equal to R2 because R2 minus something positive, something non-negative here, you see, greater than or equal to 0. So what's the conclusion? B is less than or equal to R2, or R2 is greater than or equal to B. But that's a contradiction because R2 was assumed to be less than B. You see, R1 is greater than or equal to 0, we assume, so R2 minus R1 is less than or equal to R2. And then B is less than R2 minus R1 because B divides R2 minus R1. And they're both positive integers. So the smallest I can multiply is 1. I cannot multiply by 0. B times 0 is 0. In that case, R2 minus R1 is 0, so they are the same. Then Q1 and Q2 are the same. We go into this. So B is less than or equal to R2, and there goes a contradiction. So R1 and R2 cannot be different. They must be the same. If they are the same, then Q1 and Q2 are the same as well. Therefore, even if we have two pairs, Q1 R1 and Q2 R2, they are the same. And there goes the uniqueness. Quotient and remainders, Q and R, not only exist with these properties, blue and green, but they are unique. That completes the proof of the division algorithm.